Hello friends, I am Amir Nizami and today we are going to study quasi-3 dimensional theory for laminated composite beam. So let's start. So first of all, we can say that in the last previous classes, for we have studied for the beam theory as CLPT beam theory, okay, then FSDT, then we have also studied third order shear deformation TSDT, and today we are going to study the quasi three-dimensional theory, quasi 3D theory, and inshallah in the next class we will study the zigzag theory for the beam, zigzag theory for the beam. So these three are almost we have covered. Today we will cover inshallah this quasi 3D, and in the next class we will cover the zigzag. So now we are just going to start with the quasi three-dimensional theory. So these are the displacement field for quasi 3D theory. Quasi 3D theory. So we can see here the displacement field for the beam u of xz is written as u naught of x plus z times minus del wb by del x plus f of z into minus del ws by del x, and then w of xz is written as wb of x plus gz into ws of x. Here basically this displacement field w, we can see that it's a function of wb of x plus gz times ws of x. So this g is a function of z, and here we can see that this w of xz is not only function of x but it's a function of z also. Okay, so therefore we can say that here this displacement field would have the stretching. Epsilon zz would be allowed because del w of xz by del z would be equals to, if we differentiate with respect to this, so this would be 0 but this would be remain there, del g of z by del z into ws of x. Okay. So here stretching is allowed. So therefore in quasi three-dimensional theory we know that epsilon zz that's not equal to 0. So this means that stretching is allowed. Okay, now it's a generalized displacement fields written here. If we put fz equals 0 and gz also equals to 0, so then we will see this fz equals to 0 and gz equals to 0, it is written as u of x is u naught of x minus z times del wb by del x, and w of x equals to wb of x. So we are aware of this formula. So in the classical laminated plate theory we have seen this formula. Okay, now here if we put fz equals to 0, okay, fz equals to 0 and gz equals to 1, so it becomes simple first order shear deformation theory. Okay, another case we can see, one of the case is there that where we are considering f of z as z into 1 minus 4z square by 3h square, or we can also consider the trigonometric function like this. So we can put here fz is this and gz equals to 0. So if we put gz equals to 0, then we can say this would become the third order shear deformation theory for the red d third order shear deformation theory. If we put z equals to this, okay, or another trigonometric shear deformation theory, this would be trigonometric shear deformation theory if we put this, and that is we can say these are the higher order shear deformation theory. Okay, now we are going to study the general case of the quasi 3D theory. So therefore we are considering here f of z as well as g of z. Okay, so here our gz function is also available as well as fz. So we are going to study generalized quasi three-dimensional theory. So if we see that the displacement field strain displacement relation epsilon xx is nothing but del u of xz by del x. So if we differentiate and put the value of u of xz here from this equation 1. So it would be equals to del u naught of del by del x plus z times this minus del 2 wv by del x square plus fz times this minus del 2 ws by del x square. Similarly, epsilon z would be equals to del w by del z. So if we differentiate, so this portion would become 0. So the first part is 0 plus del g by del z into ws of x. Then gamma of xz, that's the shear strain, transverse shear strain, del u by del z plus del w by del x, and finally we get this, that is the gamma of xz. Now we also know the stress strain constitutive relations. So now we will apply that. Sigma xx equals to q11 of k into epsilon xx plus q16 of k into epsilon zz. Okay. Similarly, sigma zz, that's equals to q16 of k epsilon xx plus q66 of k epsilon zz. And sigma xz, that's the transverse shear stress, that's equals to q44 of k into gamma xz. Okay. Now we will just uh, write sigma xx by expanding, keeping the value, substituting the value here. So epsilon xx is nothing but del u naught by del x plus z times this plus fz times this. So we are just keeping the whole value of the epsilon xx plus q16, that's written here q16 times epsilon zz, and we have already seen epsilon zz is del g by del z into ws of x. Now sigma zz we can also write in the same way, q16 epsilon xx plus q6 epsilon zz, where we will keep back epsilon xx and then we will keep the value of epsilon zz. Then sigma of xz, so here we can see q44 of k into, we will just substitute gamma of xz, so we will just put the value. So we get these three relations for the stresses. Now we will apply the principle of virtual work. So we know that net internal virtual work done minus external virtual work done equals to 0. So therefore internal virtual work done is nothing but stress times strain into volume integral. So this volume integral we can say first areal into this z height into sigma xx delta epsilon xx plus sigma zz delta epsilon zz plus sigma xz delta gamma xz dz. Now we will just do the first part. So we will take this one and we will integrate with respect to z. Okay, so we are just doing that. So sigma xx into, we are just taking del of epsilon xx. So we know epsilon xx from back equation, so we are just substituting variational of that. So del of del u naught by del x plus z times minus of del 2 of del w by del x square plus fz times minus del 2 del of ws of x upon del x square. Similarly, we will multiply sigma xx and integrate with respect to z, and we are just keeping it out of the integration of z because it is free from the z coordinate, so it's only a function of x. So therefore we are just taking out of the integration of z. Okay, plus z times sigma xx dz, and again we are taking out this del 2 wv del of del wv by del x square because it's a function of x only. So we have taken out from the integration of z. And similarly fz times sigma xx dz into this we have taken out from the integration equation. Okay, now we have written again the same sigma xx dz and all. So we know that integration of this sigma xx dz we are writing as nxx, force resultants. Again, if we say z times sigma xx and integration of this, so we are writing it as mxx. Okay, mxx times this del w, the derivative, second derivative of wbx square, and then fz times sigma xx and integrating with respect to z, so we have written it as p of xx. Okay, now again from the principle of virtual work, now we are working for the second part, sigma zz into delta epsilon zz. We have already done this and we are going to do now this. So we will start by doing integrating with respect to z. So we have written here sigma zz into del g by del z into zz, and we have taken out the function of x outside integration. So we have just given the name of this integration as s of zz into delta ws of x. Now again, from the principle of virtual, our third part is this, because we have already done these two. So now we are left with this sigma x into this. So now we will integrate this sigma x into delta gamma x. So after integration, we are just integrating here. Okay, so the this portion came out from the integration, and we are getting sigma x into delta. Okay, now substituting equation 9 and 9b and 9c back. So we will just substitute it. So we are getting here internal work done. So by just substituting nxx into this mxx pxx sz and sxz. Okay, so after integration by parts, if we just integrate, we do the integration by parts for this. So we will left with this is the b, which is the width, where we have obtained by integrating with respect to y coordinate. So we have directly taken b, width of the beam. And now uh, after integration by parts, we are getting this plus the boundary terms, which I haven't written, boundary terms. Okay, and the external work done, we know that the q naught of x into variation of the displacements, transverse displacements. Okay, so now we have already used this nxx nyy, but how it came, so what's the value? So basically, if we see, nxx was nothing but integration of sigma xx dz. Okay, so if we say sigma xx, if you remember, then it was nothing but q11 of k into epsilon xx plus q16 of k into epsilon zz, and we will put back the value of epsilon xx and epsilon zz in that. So if we put back the value, so q11 k dz into del u naught by del x, this came out, and we will integrate this. Similarly, plus z times q11 k dz into this, plus fz times this, and then del gz by del z into this times w of s. So now if we see, this become a1, and the integration of this part, okay, this become b1, and then this integration fz times q11 k dz becomes c1, and this integration part, okay, which is a function of the material properties and z, that becomes d1. Okay, so this is the nxx. Then in the same way, mxx, we have just z into sigma xx dz. So we have just open all the terms, and we get b1 times this plus e1 times this plus f1 times this and g1 times this. Again, further, p of xx, that's fz times sigma xx, and again we will expand with the same way. Okay, so we will get c1 f1 h1 and j1. Now szz, so that sigma zz into del g by del c. Okay, with respect to dz we will integrate. So we will get in the same way d11 del u naught by del x plus g1 plus j1 plus l1. So these are the values we are getting. Okay, s of xz, so this as we are writing this as a as, which is the material properties and the coordinates, transverse coordinates. Okay, now we have arranged in the matrix form here. So nxx, mxx, pxx and sz is written in this way, and these are the strain and curvatures. Similarly, sxz is nothing but as times del ws by del x. Okay, so we have seen here, and now we will substitute the value of nxx, mxx, pxx, sz and sxz back in the governing equations, where we have seen here. We will keep the values of nxx, mxx, pxx, okay, and sz and del sxz del z. So if you will put this and just equate the formula, then we will get the governing equation respect to u naught of x Okay, then you can say wb of x, and then you will get with respect to delta ws of x. Okay, three governing equations you will get from here. So three unknowns, three governing equation. Okay, so we will see the code now. Okay, so we will see Quasi-3D beam code. So if we will run this code, let's see the results. Okay, so we have run this in Mathematica. Let's see. So this is the transverse displacements we are getting w. Okay, this is the in plane displacements u. Okay, this is the gamma xc, and this is the sigma xc from the constitutive equations, which is showing the jump at the interfaces, as we know. And this is the sigma xx, sigma zz, and we are getting this sigma xz from the equilibrium equations, which is continuous throughout the interfaces. Okay, thickness. So at the interfaces also it is continuous, as we have found it from the equilibrium, integrating the equilibrium equations. So we will stop here, and inshallah in the next class we will cover the zigzag theorem for the beam.